Good afternoon. This is David Eastwood, Geotech Engineering and Testing. Thank you for sharing your afternoon with me. Thanks ASCE, American Society of Civil Engineers, for sponsoring this program. Today's presentation is about forensic evaluation of structures. It applies really to residential, commercial, light industrial, anything light structures. So that's what it involves in. Audience, we got about 210 people and lots of civil engineers, structural engineers, forensic engineers, architects. So people from all kinds of cities and municipalities, inspectors, structural engineers. So if you need to reach me, my email is de@geotecheng.com. My phone number is 713-699-4000. This is going to be on YouTube, and there's a lot of information on this presentation. So you're not going to catch it all in one shot. So you really need to watch it several times on YouTube to kind of get an understanding of what I'm talking about here. But at least you will hit the highlights. I hit the highlights on this presentation. If you have questions, please type in your questions in the Q&A segment of the presentation. I work for a company called Geotech Engineering and Testing. We've been in business for about 38 years. And we do geotechnical, environmental materials, and for geoforensic engineering. We have a staff of 60 engineers. And the support staff, we work all over Texas, Louisiana, Oklahoma, and New Mexico. We have our own drill rigs, so we can mobilize quickly on projects. When you do forensic engineering, you can do anything from a school project to a police station. This is the city of Houston police station on Wilcrest, to a custom home. You're going to see cracks and distress all over the place. The Italians can do wine, but foundations, they got problems with foundations. These are some design errors. You can see these guys didn't pay attention to their design. If you go to the campus of Rice University, you see a lot of cracks out there in their block wall systems. Some more cracks in the block wall. Cracks in the brick. There's an apartment complex out there in Stafford. You got crack at the top. That means you got tension at the top, compression at the bottom. It's wider here. More cracks. This is near Galveston Strand. It's a commercial building with cracks and separations. More separation, commercial building. Crack in the wall. Residential project. Cracks in the wall. Brick. More brick cracking. This is a church in Bel Air. A lot of cracks in it. Great beam cracking. Floor slab distress. You got Sam's Club. You got cracks in the floor slabs. If you look at the Sam's Club and you go look at the slabs a lot of times, you see all these little cracks out there in the floor slabs. That's called crazing. And they result of repeated high traffic areas. Lots of people walking around with their shopping cart and stuff like that. And it's not easy to repair them, I guess. You can put a overlay on it or remove and of course replace it, but it's not easily repairable. Here's a crack out there in the brick. You can stick your hand in. This is some exterior cracking. You can see separation, shrinkage cracks. cracks in the brick. Here are interior cracks, a lot of sheetrock cracks, doors not being square. More sheetrock cracked. This is a sheetrock crack in the medical facility out there in Stafford. See a lot of ceiling cracks. This is a sheetrock crack. More cracks interior. See the ceiling panels are coming apart. It's a medical facility, City Houston Police Station. The floor slab is heaving. The wall is bulging. Doesn't have any place to go. Wall bulging here. This is a school bathroom. You can see the cracks in the tiles. Doors not being square. You can't close them. Doors not square. This is a medical facility in Stafford. It moved so much to broke the glass here. So people get in this way. They don't use the door anymore. It's a floor slab separating from the wall here. Same medical facility out there in Stafford. Spread footing. These guys were leveling a slab. They put them on a spread footing on top of expansive soils. And expansive soils heaved up, and you can see all the floor slabs have heaved up at where they put the spread footing. So subdivision. Some of these subdivisions, they go in there and turn on the sprinkler system. Soils are sandy. When they get saturated, they start settling. So the sidewalks start settling. Brand new subdivision. Sidewalk settlements. Overwatering of the grass. See the grass is settling. Small area. This is a Montessori school out there on Willcrest. We couldn't close the door. Lots of movement. Moisture coming through the slab. We see a lot of these projects with moisture coming through the floor slabs. It's bulging up the slab. You see the covering is all cracking up and heaving up. This building here is a warehouse building. This side, they had moisture barrier underneath the concrete. Here, they didn't have a moisture barrier. So it's always stayed wet here. And they asked me what to do. I said, you have to remove it or replace it or put some kind of sealant on it. Can be easily solve the problem. You dig in there underneath the floor slabs, you see water just sitting underneath the floor slab. A perch water table. Tiles, we see a lot of tiles separating or cracking. This is an exclusive furniture project in Rosenberg. Grade beam cracking at the corners. That's because of the absence of bond breaker between the brick and the concrete beam. Yeah, it moved thermally at the different rates. So when there's a shrinkage and expansion, the concrete here breaks. It's not structural. It can be removed and place a bonding agent there and put in a non-shrink route and put the grade beam back together. Slope failures. This is a medical. This is a Memorial Drive out there near River Oaks area. This Buffalo Bayou. It's the doctor's house. The whole backyard is failing. And here's another one failure. See the house is sliding down. The pavement area failing. Retaining wall failures. This is a wall that's kind of subject to hurricane loading. During the hurricane, water just kind of washed up the wall and developed cracks in it. This is San Antonio. You can see the wall in here cracked up. About 250 homeowners were impacted. This is a MSC wall, mechanically stabilized block wall system. It failed, and the whole backyard starts failing. And you can see that the wall is moving and the backyard is failing. Pretty bad situation there. See the AC units. This is out there again, wall failure. Houses out there in Lake Conroe 105. These guys were digging this ditch to connect to the lake so that they can park their boat in there. So as they dig that out, the wall starts moving and the failing. They were connecting this ditch to this little canal here. And the whole backyard starts moving. The pools in the backyard start moving. More bulkheads. This is a bulkhead out there in League City area, Texas City. This bulkhead starts moving here, starts failing, and it starts moving. The whole backyard here starts moving. See the separation here? So they had all this stuff in the backyard, and you can see that the stuff starts cracking and separating. So the whole thing started moving. There's a crack out there in the grass in the backyard. More bulkhead failure. This is near 610 Loop, near Galleria. The round building we have out there, 610 and 290 area. I-610 and I-10 area. Here's another bulkhead out there near Colorado River. The water went up, went down. It's called rapid drawdown. And the bulkhead failed. You can see the whole anchoring system failing. Here's another bulkhead terminal here for a port facility. They went in there and started loading it up. And they start put gravel on it. And as they put that on there, it was too heavy and just the whole thing just caved in. We see a lot of the channel failures because of dispersive soils soils that are easily erodible when they get wet. These soils contain high percentage of sodium ions. And you can see that dispersive soil in here. These little holes in here, the little tunnels. Water washes them out. The soils, they call it jug holes. So Harris County Flood Control Project, you see the dispersive soils. This is out there, Veterans Memorial and Beltway 8. There's a subdivision there. The detention ponds start failing due to dispersive soils, develop all these little holes in there, jug holes. The cops were chasing somebody. The guy falls into one of those holes, breaks his back. Buffalo Bayou out there on San Felipe, this beautiful golf course out there. Right next to Buffalo Bayou, they were dressing up the slopes in here with geogrids and for grass growing on it, geotextiles. And what happened was they didn't check for global stability. Then all of a sudden, the whole thing starts failing. So it's a slope failure. See the red line? You can play golf past this red line. See a bunch of lawyers here. So failure comes in many shapes or forms. These are the slope failure pictures. This is China. They had this building over here sitting on piles. They start digging in front of it. The building falls. And I think one person dies. Start digging in the front, stockpiling here, causing surcharge and breaking up the piles, and the building starts falling. Geologic faulting, and we have a lot of faults in the Houston area. Building houses on top of the buildings on top of the faults. See the delineation of the fault. Pools, we have a lot of pool failures in Houston. They're not building these pools properly. They don't engineer them right. They don't build them right. Parking lot failure, punch through failure. This is the project in Dubai out there. They start excavating this area next to a river. Water starts coming in. They didn't take care of it. And the whole thing opens up. These guys are still in here. We see crane failures a lot lately. They're bringing these cranes out there, building this concrete here, 2 yards of concrete. That's about 8,000 pounds. And they start delivering it down. That's Texas Medical Center. The outriggers go into the soil because of the bearing capacity. They fail. And then somebody gets hurt. Whitney Lake, failure, slope. They built these houses here. We got a crack right here. Starts failing. Effervescence. You go out there, build the stuff with brick, and they use mortar that's got high alkaline mortar in it. You get this white powdery stuff on the brick. Called effervescence. Effervescence is a fine white powdery deposit of the water-soluble salts left on the surface of the brick as the water evaporates. To have effervescence, you should have water-soluble salts that present in the wall. Must have a sufficient moisture in the wall to render the salts in a soluble solution, and there should be a pathway for it to come to the surface and dry up. Usually sources of effervescence are because of alkali sodium sulfates and potassium sulfates. To reduce the chances of effervescence, of course, you use a low alkaline Portland cement that has 0.6% alkali or less by weight. Concrete pavements, we see a lot of pavements with distress. A lot of concrete, you got alligator cracking out there. No steel in the paving. This is the paving out there for the Marriott out there on West Loop. Joint failure. A lot of these expansion joints fail, starts pumping. Cracks in the paving itself. The shrinkage cracks. All kinds of weatherings and pop outs. You can see the cracks in the paving all over the place. Concrete paving. The black stuff is coming out through the concrete is all the soils that's seeping through the subgrade into the pavement areas. Expansion joints whitening. This is Flower Mound near Dallas. Again, more pavement cracks out there. This is a Wilcrest. The Montessori School. Cracks in the pavements. Not that many control joints. Asphalt pavements. This is near the Bush Airport. They put asphalt here with not much of a base and the subgrade stabilization. So this is a parking facility. Developed many cracks and distress. So what is failure? Failure is defined as a function, as a foundation structure, component, or a facility that does not perform as intended. The failure does not have to involve collapse or catastrophic events. Some examples of the failure are foundation that exhibits excessive foundation movement, parking lots that pond water, roof that has excessive deflection, masonry wall that cracks because of lack of expansion joints, basement walls that leak, pools that are moving up and down, slope failures. Most failures are not on evening news, but they're important to the building owner that has to deal with the cracked foundation walls. The contractor has to repair it. The engineer will get sued for faulty design, and the attorneys will make the money. The way you determine the causation evaluation of the forensic project, you look at the problem, you state your problem, perform observations, formulate hypothesis to the cause of the problem, test the hypothesis by observations, analysis, testing, analyze the results, make final conclusions. And you develop a damage model. Damage model tells you how much it costs to fix the problem area. So if you got a foundation problem, you say, okay, you got to fix it by underpinning. This is the kind of underpinning you use. This is how much it costs to do it. It's called damage model. Qualifications of the forensic engineer. You have to have formal education, experience. You got to be licensed engineer, active in social technical societies, fair, truthful, objective, avoid conflict of interest. Got to be like a detective. Detective is somebody whose job is to discover information about crimes and find out who's responsible for them. You have to be able to think outside the box. You must enjoy digging for the truth. Got to be a good communicator. You got to be able to do reports and presentations, deposition, trials, all that kind of stuff. Usually the reasons for foundation failures are bad design, inadequate geotechnical report, inadequate structural design, construction, materials, bad materials used, construction didn't follow plans and specifications. There were bad maintenance around the buildings. You had trees, drainage, other wear and tear, sewer leak, plumbing leak, inadequate geotechnical report. So you have describing an inadequate site conditions and description. For example, if you have slopes on the site, not describing the bearing capacity of the soils. If the soil is saturated, the bearing capacity is lower. Footing depth. The footing for the structure should be found in expansive soils. We're finding out the drill piers for a lot of the structures are too shallow. In Houston area, for example, the pier depths in areas where you got highly expansive soil should be 18, 20 foot deep. You put them at 12 foot deep, 13 foot deep. That's too shallow. Incorrectly estimated movement values. When you come up with how much PVR you have, potential vertical rise, or Y sub M values for post-tension slab, you got to know what you're doing. Inadequate information regarding perch water table. Parts of Houston, like in Katy area, you have perch water table, and I'm going to talk about it in a minute. Inadequate structural design. Did not discuss foundations and risk with the client. If you doing the building, you need to talk to your client about foundations and risks. If you want a cheap foundation, you're going to have higher risk of movement. If you want to have more expensive foundations, you have less risk of movement. Unfamiliarity with the proper design methods. If you're doing buildings, you got to make sure you got a structural engineer and a soils engineer that do buildings. Typically, if you do petrochemical design, you're not very good with buildings, especially residential. Foundation design without the soil report, that's a no-no. You must have a soil report every time you do a design for pavements and foundations. Misapplication of the design to site conditions, slope sites, sites on faults, wrong type of foundations for soils. That's again, a lot of structural engineers don't look at a site. So the Geotech should have pictures of the site in there. And if there are slopes out there, they need to bring it up. If there are sites on faulting, you got to do a phase 1 fault study on projects to evaluate if there are faults there. You cannot use certain type of foundations for certain type of soils. If your soil has got a PVR of 6 inches, then you cannot use a slab on grade on it unless you do modifications. This is important. Engineer of the record, who is the structural engineer in this case, should have adequate knowledge information including drainage, slopes, existing trees, future trees, and vegetation prior to foundation design. Somebody was telling me the other day, soil reports are only recommendations. The structural engineer who seals the drawings is the one who is actually doing the design. So I don't know, it's more liability for structural guys. Inadequate construction. You go ahead and do the plans and specs, and the contractor doesn't follow the plans and the specs. For example, you got a building that's got movements. You go out there and try to expose the piers and the grade beams to see how they meet the project specifications. Here you're measuring the beam depths. If the design says the beam's supposed to be 24 inches, and if it's 18 inches, you got a construction defect. Here's it trying to meet the beam depth again. Beam width. If your beam's supposed to be 12 inches wide and it's only 10 inches, well, that affects the stiffness of that slab. That's a construction defect. Again, measuring here the beam width here, checking for piers. Make sure the piers are out there. You drill holes next to the foundations to look for presence of piers. This is the pier. This is the bell. This is the distance from the tip of the bell to the shaft. Try to make sure you got the right size bell on this pier and how deep it is. So if your bell is too shallow, here's the pier. Here's the tip of the bell. And you measure it to see what size. This is at 20 inches from here to here. So from that, you can determine your bell size. For example, if this distance was 12 inches, that would be a 36-inch diameter bell. This is the shaft. This is where the tip of the bell is. This is the whole pier exposed, and there's a void in the bottom of the pier. That means when pier was too shallow, the expansive soil lifted up the pier, pushed the building up. Okay, that's what happens when you have expansive soils. It grabs the pier and pushes it up. Here's the void out there underneath the bell. Well, this is a straight shaft, underneath the straight shaft. Now, if this foundation is moving and you expose the pier and the grade beam and they're connected together, that means the piers are too shallow. When they're together and it's moving up, that means the piers are too shallow. Now, if you got your pier here, there's a space between the pier and your foundation grade beam. That means the beam itself, grade beam, is moving up and down and the piers are deep enough. Here's some sound walls in Pearland. We're driving up there and they were moving. You can see the piers coming out of the ground. These are shallow piers. They're lifting up these big panels. Columns, if you look at some of these parking garages, they need to have joints around them, parking in the columns. If you don't have joints, you start having cracks out there because columns and pavements move at different rates. So some people go saw cut, jackhammer around the columns to allow the pavement move around it. The column itself doesn't move very much. It's the pavements around it that's moving. Here's this is a new commercial building out there. They are putting booths out there. around the column as a joint. These are the boots, rubber boots. And as a joint between the columns and the foundations. Here are some of the joints out there. They're put in for columns nowadays, diamond shape or circular shape. Instrumentation, you can measure the crack movements by crack monitors. This is a two-dimensional movement. Crack monitors. You see the separation in the sheetrock. These are the crack monitors. This is a three-dimensional crack monitor system that shows the movement of the crack in 3 dimensions. Non-destructive testing, you can use ferroscan or GPR, ground penetrating radar. This is a warehouse building. We wanted to know if there's a steel in the concrete. So we're using this system here is just like a GPR ferroscan. It uses electromagnetic field, and you just run it out there on the concrete, and you can read on the concrete on the screen where the steel is and the size of the steel. In this case, you can look at it here. The steel's 10.5-inch spacing, 8.5-inch spacing this way, 10.5 spacing this way. It's a number 5 bar. Here's another warehouse building, trying to figure out if there's a steel in the floor. We go out there and core the area with concrete cores to calibrate the machine. And then measure the pavements and steel locations. And you can see here the steel is 12.5 inches apart, 11.5. This spec calls for 10 inches apart. Here's about 10, 12 inches apart. And the spec calls for the slab to be 8 inches and the steel be 2 inches from the top. In this case, the steel is 3.6 inches, 3.5 inches from the top. So it's below where it was supposed to be. Sometimes we find steel on the bottom of the slabs. They don't put chairs in it, and you can see the steel all the way in the bottom when you excavate under the slabs. It's not doing anything for your steel, for your slab. It's not holding the concrete together. Sonic testing, you can use sound going through concrete. The typical concrete sound travels at the rate of 10,000 to 14,000 feet per second through concrete. Yes, this thing here is this little plate, hits on the concrete and sends a sound. You can read here that device, how fast it's going. And from that, you can calculate the thickness of the concrete. You have to calibrate that machine with the existing cores. You core the concrete. You calibrate the thickness with your machine. You put the machine right in here and calibrate it, make sure it's correct reading. Here's that you can see in here on this slab in here. The slab is supposed to be 6 inches. Here's 5.2, 4.39, 5.3, 4.1. You see a lot of places here that are in pink. The slab thickness is less than the specs. The tolerance for a slab is thickness is +3/8 and minus 1/4 of an inch. That means when you pour a slab, it should not be thicker than 3/8 of an inch than the specs and 1/4 of an inch less. So if you're pouring a 6-inch slab, it should not be more than 6 3/8 and less than 5.75 inches in thickness. Here's again using our device here to measure the pavement thickness. We core the concrete, calibrate the machine with the actual core, the thicknesses, and you get this area, the concrete's supposed to be 8 inches. It's 7.9, 7.9, 7.86, 7.91. Here, concrete's supposed to be 6 inches. It's 5.86, 5.2, 5.73. So a lot of places, the pavement thickness fails. Here's supposed to be 5 inches, some areas. is 3.83 inches, 4.1. So there's a device here using sound velocity in the concrete to give you pavement thicknesses using non-destructive testing. We'll also do geotechnical sampling to see what kind of soils you have for buildings that are cracked up. We do the borings next to the biggest tree on the properties. Trees tell us where your foundation for a building should be. That's because of the presence of root fibers. So we do the borings. This is a portable rig. You look for root fibers. You cord it first. The cord drops, that maybe there's a void under the slab. You measure the void. If there's a crack in the slab, you put a camera underneath the slab and you can see the crack. Here's the crack in the slab. This is the vapor barrier that's kind of deteriorated. Here's we're coring the concrete again. This is the crack in the concrete slab. We're actually trying to get samples here. It's an auto zone. That's what the soil sample looks like when it comes out of the ground. This is a house in Seabrook. A lot of foundation problems. They didn't do any geotechnical work. They put the piers at 8 feet. The house started moving. Highly expansive soils. You go inside out there, start drilling, see what kind of soils you have underneath it. That's the kind of soils you get, really nice fat clays. Elevations. As one way to evaluate the forensic evaluation of foundations is you got to know what the elevations of your slab is. How is it moving? Now you measure it by elevations. You put the elevations out there, machine zip lock, zip level. You put it on the slab and you measure the elevations. Sometimes you can put a device we call slab shore. You put these cables in your beams as you build a slab, and that gives you these blue beams. The cables can give you elevations permanently in your slab. That's what they look like. Where you put your cables in, or after you build a slab, you can put them around the perimeter. It's a slab shore, the monitor system. You screw it out there to the exterior grade beam. So you excavate, you put in your cable, you put soil back in, connected to this monitoring system. This monitoring system sends a signal to your phone and tells you any kind of a movement that you may have around the house or any kind of a building. And it's permanently, you can watch it. If there's any movements, then you can do more elevation measurements. But this is a really good system to evaluate the slab movements called slab shore. You can develop contours of your slab where it's heaving or settling. This is a house, was built. There was a tree taken out before the house was built. If you look at the elevations of it, this side is minus 0.2. This side is minus 2.4. This side's got highly expansive soils. So what happens? Well, if it's a minus 0.2 here, that means this area here is heaving compared to here. This is where the tree used to be. So that's the heaving area. Here's the medical facility again. You can see the slope moving down from 3.75 to about 0.5 inches. This is another building. You can see the contours. These gray areas are heaving. This is elevation 1.6 all the way down to 1.8. The red areas are the lower areas. The gray areas was heating. It's almost 3 inches of differential movement across the slab. This is a tilt wall building on Richmond Avenue. This was the area that was heavily wooded when they cut the trees before they built this thing. The tilt wall panels are kicking out. This is the floor slab elevations, plus 3/8 of an inch, 3/38, all the way to minus 7/8. This is the warehouse. These are the offices. So there's a lot of movements here. Outer levelness of 4.25 inches. If you do a three-dimensional slab of elevations, that's what the slab looks like. This is an HISD school project out there in near Pearland area on South Houston. And you can see about 5 inches of movement all the way minus 5.38 to minus 0.3, almost 5 inches of movement across this thing out of levelness. Here's some concepts. Tilt. Tilt is y over x, which is basically deflection over horizontal distance between the 2 points that it occurs. There's an allowable tilt of 1% by ASCE. Then there's another concept called slope, which is you can take any 2 points. It's the differential movement elevation between 2 points divided by the horizontal distance. The distance between them is called slope. But your tilt is about 1%. Slope of 1%. So if you got a house and you got elevations like that, if you plot them, you see they're parallel. The fact that they're parallel, that means they're tilt. You can have up to 1% tilt. If a building tilts, it doesn't crack. Okay, it's not differential movement. You can have up to 1% tilt. Here's a concept called deformation, which is change of the shape of the foundation after the original foundation construction. Deflection is the maximum deviation from a straight line between 2 points. Deflection ratio is deflection divided by a horizontal distance over which the deflection occurs. So if you measure the deflection between points 1 and 3, it's right here is 0.2. You got 3 points. This is deflection. This is not the deflection. It's not correct. It's the correct deflection. PTI has got a guideline for design of the slab on grade and deflections. Also, FPA, Foundation Performance Association, has that. Basically, they say your deflection is L over 360. That's 1 inch and 30 feet. Your tilt is 1%. That's allowable deflection. So if you got a house or a building that's moving, you do a section BB here on the elevations. You plot that section. You find out that the deflection is L over 563. That's very small, smaller than L over 36, so that the deflection passes. The tilt is 0.38%, 38%. Less than 1%, it passes. You run another section here, section 8AA. That's the deflection. The maximum deflection is L over 318, which is bigger than L over 316. So your deflection fails. The tilt is 0.13%, less than 1%, it passes. Now, there is some dispute going on about this methodology. ASC is looking at this thing here. There's been a paper published on this thing. But a lot of the structural engineers use this method. but there's a dispute about it right now. I had a question in here. Okay, let's see. Mike is asking a question. Can you comment on allegation that what the method you just submitted is not in conformance with introductory engineering scientific principles? So Mike here is saying that he's one of the guys who disputes this procedure. Again, ASC is looking at this thing here. They haven't come up with a final judgment, but FPA and also PTI, Positioning Institute, they're using this method. If anybody's got any question about this dispute and all that, send me an email. I'll refer you to Mike. He's an expert on that, so he can probably bring you up to date on this thing. TRCC performance and standards. Floor slab crack sizes. If the crack sizes are more than 1/8 of an inch in floor slabs, that's considered construction defect. If your flat work crack size more than 0.25 inches, that's too big. Expansion joints more than 1 inch for flat work, that's excessive. Stairs 3/8 of an inch. Carport garage separation 3/16. Sheetrock 1/32. Brick masonry is 1/8 of an inch. Separation in the brick. Joints in the brick mortar no more than 1/4 of an inch separation. Some remedial measures, if you got a floating slab foundations and you don't want it to move, is you can use a sprinkler system around it, all around it, so you have uniform moisture so it doesn't move. Plus, place space between the driveway and exterior beams. Have positive drainage. Do not use sand in your foundation system in the forms. You can remove the expansive soils and place non-expansive soils, which is expensive. Nobody does that. So if you got a soil with PI of 60, an active movement zone of 10 feet, you need to move 7 foot of soil for it to get the PVR to about 1 inch. This is select fill that you can put under the slab to make it not move as much. Select fill has got a liquid limit less than 40, PI between 12 and 20. Here's a bank building. You can see here, this is paved here with concrete. Here is grass. This area, because of change in moisture, is going to move. This area does not move because it's concrete covered. So you're going to develop cracks here. And you can see in here, this side has got all grass. This side is concrete. Then you may develop cracks over here because of differential movements. It's a blockbuster building here back in the old days. You have grass all around it. So you have uniform moisture. When you have uniform moisture, you have less chance of movements. When you put driveways, put a separation between the driveway and the house so that you have uniform moisture around the house. If you put the driveway right next to the house, this side of the house is not going to move. This side is going to move where you got grass, shrubs and grass. Develop differential movement, so it's going to crack. Cleaners. This guy here, they put concrete all around the building. So in this case, once the building becomes stabilized after initial movement, it doesn't move anymore because there's no change in moisture. Remember, movement occurs because of change in moisture. If your moisture doesn't change, it does not move. So usually major movements occurs when the soil goes from all the way from dry to wet or from wet to dry. So that's what happens. But if your moisture doesn't move, you don't have to worry about movements. If you want to know exact movements of a building, you put a benchmark into place. Benchmark is a fixed point that doesn't move. So you dig a hole in the ground about 20 foot deep. You drill the hole, you put helical piles in it. You put them in down about 20 feet. This is the pile, it's connected to the soil at 20 feet. It's not in connection with any soil around it. Then put PVC around it. Then you fill in the area between the PVC and the soil with grout. This becomes a fixed point that's connected below the active movement active zone. So it doesn't move. So you can use that as a benchmark here, measure elevations around inside the building. Here's a building in San Antonio. These are contours of the elevations. And when you look at the elevations and you see the slab is moving, you know, November, August, March, each one of them, you got different elevations. So the slab moves seasonally. Perch water table, parts of Houston, for example, we got near Katy, sand over clay, or in the woodlands, Bridgeland. This sand over clay, the water sits in the sand, cannot penetrate the clay. It develops a bathtub effect. It just soil gets all saturated. Soil starts pumping. Here. So if you go out there and start digging your beams out there for your residential or commercial building, the beam gets filled up with water. This is called perched water table, and that you develop that by having sand over clay. Okay, so you will have perched water table on the around piers, on the tit wall building, in your planted areas, especially when you go dig out next to some of these houses, and you see water is coming up under the slab. It's because of the presence of perched water table. Water is trapped underneath the slab, causes the expansive soils to move. If you want to know water levels underneath your slab, you do piezometers. You drill a hole in the ground about 10, 20 feet deep, like 20 foot deep. You put this PVC pipe about 2 inches in diameter. It's perforated. You put it in there, put sand around it. And you can measure the water table here is 7 foot where the water table is in the hole underneath the slab. This one here has got 10 foot. This one here is 13 foot. That's a piezometer. You can put it inside, you can put it outside and measure water levels. On this specific building, the water on the slab was like 7 foot, but outside the slab was like 18 foot. So water was trapped under the slab. The way you make a piezometer, you got your screen, and then you put it in the ground about 20 feet. You put sand around it. Above that, you put bentonite balls. Above that, you grout it all the way to the surface. That's basically called a piezometer to measure water levels. If you got a post station slab, you want to know if your cables and your slabs are good or bad, you do what's called liftoff testing. You test the cables, you lift them up. The purpose of liftoff testing is to verify that the design force in the tendon has been achieved. So you did basically you get the end of your cable out there on the live end of it, you expose that. This is your cable in your post tension slab. You do this for a lot for apartments or residential foundations. You grab that cable and you start pulling it out with the jack. And you make sure you got about 26.5 kips of load in it. You do 3 tests at each side of the slab. On the live ends of it. Brick. A lot of our structures are covered with brick. Good exterior, beautiful, lasts for a long time. But you see a lot of cracks. Here's the whole building here. There's a crack right there. I mean, a joint right in there in the middle of it. That's the joint. Here's a brick cracking here. There's no joints in this brick wall in here. No joints. There got to be a joint here. Here's a brick joint right there. It's another brick joint. Here's a saw cut brick joint. We put it in on a building out there at West University. Why do we need expansion joints in brick? Because brick and building materials expand and shrink with changes in temperature, humidity, and other environmental conditions. Because those materials move at different rates, because nature will put them in if you forget to put it in. Where to put the expansion joints? In brick or masonry, periodically in long walls at 20-foot spacing, at offset in walls, where the short run of a masonry meets the long runs, at outside corners where different materials meet, at junction with different functions or different heights. Brick joints is about 20-foot spacing. Here's a school project. You can see the long wall in here. It's a CMU block. See the joints? You got joints out there anywhere that's needed. Joints, 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 joints. Here are more joints. Joints in the wall, 20-foot spacing. More joints here. There's a corner here. There's a joint in the corner. There's a joint right here in this corner. So you put a lot of joints out there in your walls. Materials. Cause of failure can be because of bad materials. Inadequate concrete strength, fill that's wrong. If you've got, don't put select fill in or put sand underneath the floor slabs. Reinforcement steel, you put grade 40 where you need grade 60 steel. Is the select fill. That's what you put on your slab in your forms. Liquid limit less than 40, PI between 12 and 20. You don't put sand in it. Don't put sand in your forms because water travels through sand and gets to the expansive soil and causes it to heave. You core the slab or your pavements that are failing. Measure the concrete strength. We see where the steel is. You test your concrete in compression. You break the concrete. And basically, ACI, American Concrete Institute, it says that the concrete in an area represented by core test shall be considered structurally sound if average of 3 cores should have 85% F prime C, and no single core should drop below 75% F prime C. So if you got a slab with a design strength of 3,000 PSI, none of the cores should drop below 2250. Average of 3 cores should not drop below 2550. Petrographic analysis. Now, in that case, if your strengths drop below those values, essentially you can find, you say your slab has failed in concrete strength. If your strength passes, but you still have a bunch of cracks on your slab, you do petrographic analysis. You take a slice of the concrete here, and you put it on the, cut the concrete and you get a slice of it. This is a slice. Put it on the microscope. You inject it with blue dye. You look at it. If you look at the water cement ratio, typical concrete's got a water cement ratio of about 0.4. Here's 0.55 to 0.6. That means they added too much water to the concrete. That's why you got all that shrinkage cracks. Here you look at the crystallized in here. These are calcium hydroxide crystals. And here you got all these dirty aggregates, the black stuff. If you have a bunch of clays around your aggregates, you get high water cement ratio and lower strengths. Here's a micro crack in your concrete and your paste. So the petrographic shows you if you got high water cement ratio, if you got dirty aggregates, if you got too much fly ash, if you got problems with entrained air, void system, if you got problems with chemical attack, alkali silica reaction, ASR. ASR is a reaction between the certain aggregate types like gravel with cement that forms a gel that causes excessive expansion and pop out in the concrete. Maintenance. When you do projects, commercial, residential, make sure you have positive drainage. This is the kind of drainage you want to have. This is not a good drainage. This is not a good drainage. Not a good drainage. Not a good drainage. Yeah, we got a call from Henry here. Hello. I missed first half of this seminar to a clash. Will the recording share with someone anyway? Yeah, you're going to get a recording of the presentation. Here's the negative drainage again around this building here. Water standing, feeding the expansive soil to cause it to heave. Bad drainage here. Bad drainage in the backyard. Here's an office building on Gessner Avenue. You can see the mountain here, negative drainage towards the building. You got the tree right next to the building. This poor building is subject to so many environmental conditions. The tree and negative drainage can't get much worse. And again, you can see that again, negative drainage to the building and the trees. Here are the apartments. You got trees right next to them and negative drainage. That means the drainage is flowing towards the building, the water. Here's again, you got a real flat drainage and you got gravel next to the building. Very permeable, creates a perch water table, causes this building to heave. That's heaving actually. And you can see here, these big trees out here, good positive drainage here. The trees is kind of away from the building. Good positive drainage. Good positive drainage. Positive drainage. You got to put the trees as far away you can do from the buildings because they're going to suck moisture and cause problems. Or if they die, they cause heave. Bed liners. If for your landscaping purposes, you put bed liners in. These bed liners, if like gravelly, sandy material, topsoil in it to hold the water, causes perch water table, causes building heave. Negative drainage here to mount the bed line, the beds right next to the building at the higher elevations that the building slab is. Bed liners next to the house in Westview, the gravel. It drains, water holds in here, causes movement. Sprinkler system, bed liners next to the house in Friendswood. This is Brazoria County offices out there in Brazos, Texas. You can see topsoil here, and you got gravel here, holds the water next to the highly expansive soils underneath the building. This guy put a fish pond next to his house, highly expansive soils, bad design. AC units and condensation due to AC. And then the water just comes over there and starts to drain the water and wets the ground and causes the expansive soils to heave. Gutters, you need a splash box here. You lose bearing capacity. There's a void here. And water gets underneath the foundation. You can see it here, bad, design here again. Low area here. The gutters are coming in. It's an HISD project. Poor maintenance. You got to take that gutters into underground drainage system. These are more gutters going to an underground drainage system. These gutters are dumped right in front here in the pavers. Not a good design. It feeds the expansive soil, causes movement. Pavers are permeable. Not a good design here. You get the splash box, get that water away. This is better than nothing, really. Here's a pretty bad one out there. The gutters draining right over here into the splash boxes. Then they got these gravel all around here that holds the water very flat. Causes this building to move around quite a bit. It's a really bad design. Gutter draining right next to foundation. No splash box. Here's gutters draining into the grass. Gutters going to an underground drainage system. Good design. Gutters are going to this flexible pipe here, coming out at the curb, which is taking the water away from the building. Now, roof systems, sometimes they slope these roofs on these buildings. This roof is sloping. The building was moving, and they had gutters only on one side. This side of the building heaved up because all the water was dumped on one side of it. So the building was heaving up quite a bit because there were just gutters on one side. This is a house on 242 out there north of Woodlands. No guttering, positive drainage. Positive drainage, no guttering. But water starts dropping out there in the planter areas with bed liners. It was holding the water. The water had developed the perch water conditions under the slab. The slab was smelling because water was just sitting underneath it. It's perch water table. House with no gutters. Creates a low area next to the foundation that holds water. Here's the low area because it's so hot. The dog excavates, trying to cool off. Here's another one, the dog excavating here. This is the area of the house that the grass doesn't grow because there's not enough sunshine, so they put gravel in there, pea gravel. But if it's flat and the ground underneath it is flat, it holds water. It's a bad design. The gutter dumps the water into it. You can't see it. You got to make sure the soil underneath this thing's got positive drainage away from the house and have area drains. It's a bad design. So there's something like this. You got to have area drains. You got gutters coming in. Here, water just sitting inside the gravel. Unless you have area drains, it doesn't know where to go. Feeds the expansive soils. Gutter overflow. The gutters and the roof lines got to be designed so they can take the water. And if you get overflow in one area, that area is going to heave up and cause distress in that area of the structure. Olive Garden restaurant. This is Olive Garden restaurant in Conroe. They just built it. I went out there to start having lunch in it. Really a nice building, just built. Went out there, looked at it, went out the landscaping. You see the bed liners, you got gravel. Really bad drainage condition. If it drains, water just sits here and the bed liner would hold it in place. It's got rock exterior, which means that if there's any kind of a movement, you're going to get cracking. It's very, very stiff material with mortar. So I started taking pictures. The manager asked me, why are you taking pictures of my building? I said, man, you got really bad landscaping here. If the building starts moving, you're going to get develops in the walls and stuff. So I'm taking initial pictures so that when it cracks, we have some initial pictures of it. The gutters come in, dump over here, picks it up over here, come over here, go into an underground drainage system. This is not good. We don't want any water dumping next to the foundation. Area drains. Okay, question. Do you have an opinion about sloping a subgrade to a subgrade drain below compacted select fill? Is it really effective? We want to have a 5% slope away from a building in a grassy area and 2% if you have concrete. So say if you have a sloping subgrade to a subgrade drain below, I don't know what specifically you were saying, I guess in here, you can slope the ground to a area drain. It could be in select field. There's no problem with it. Area drains. You can see area drain here, connected with the PVC pipe. Some guys go out there and put gravel right next to their buildings. They say that's for termite control. I don't know what that is for, but it holds water next to the foundation and causes heat. You got sprinkler systems in it too. So it saturates the ground and holds water next to the foundation. It's bad design. This is Fort Bend County building. These guys, the buildings have little skirts on them. Sprinkler system. Try to keep the moisture uniform underneath the slab. It's only 2 foot. It's not very much, but it helps. See the sprinkler systems? If you put sprinkler systems, make sure it's uniform all around. Not only on just one side. It's a sprinkler system. You got concrete here, you got sprinkler system. This part of the building, it's got bed liner, gravel, sprinkler system. This part of the building can move. This is a Capital One building. They got planters here and concrete here. The building started moving. Check the planter areas. Do not use topsoil. If you have a fat clay area, you go out there and put topsoils next to the foundation, which is sandy soil, loam, and you put it right next to the foundation. This developed perch water table. The sandy soil holds water next to the foundation on top of the clays. So it's a bad practice to put topsoil next to your foundation if you have expansive soils. Grading, you want to have positive grading from a building, 5% if you have grass. Positive drainage. Positive drainage. Positive drainage with no gravel inside your bed liners. This is a building out there in Bel Air was moving the backyard. They're moving the patio, and they found a bunch of sand underneath it. It was holding water, developing perch water table, giving water to the expansive soils. Don't use sand on top of expansive soils. Structure slopes, we see a lot of residential and commercial buildings built on top of slopes in the Houston area, especially near Buffalo Bayou. You get a lot of failures. These buildings are sitting on columns. A lot of these columns are not properly designed. You can see the failures, and these guys go in there and add columns to it. See these columns, concrete columns in here. The building starts moving, developing a high moment and shear in here, and cracking the columns right there. Here's another question by Yoshira. How far should a tree be away from a house not to cause issues? What's the best mitigation ways if you do have a big tree next to a house? Okay, you're going to my next segment, so give me a minute. You got to hang in. Okay, another question here. A large volume neighborhood water well is located within few hundred yards of homes. Can this contribute to settlements? Yeah, water wells can cause what's called subsidence, which is a form of settlement. And as you take the water out, you increase the effective stress in soil, the area starts settling. Understand the aquifer is limestone in South Austin. Houses have a lot of movement with cracks. One house has the exterior piers and has seen movements in the cracks. Anyway, wells with large volume of the water cause shrinkage. Basically, this actually subsidence and settlement of the ground around it. It does that. That's why we have high levels of subsidence in Houston area, because we use a lot of groundwater. That's another presentation. So you see these houses on slopes. They're building all multi-million-dollar houses on slopes out there in Buffalo Bayou. This is at Tomball area. The whole backyard failed next to a ravine. That's me when my arm was messed up. So they had to go back and buy these houses back because the whole backyard failed. You can see if you put buildings next to a bayou, you put them on deep piers. This is Arlington Court, right next to Memorial Park. These houses like 2-3 foot spacing between them. We went out there and looked at the backyard in here. You can see the patio. This is separating from the house. There was a kind of a jerry-rigged retaining wall there behind the house. There was a bayou there behind the house. And you can see these columns starts tilting. They put sandbag, which made it heavier and made the whole patio move more. So they couldn't get equipment back there to fix this patio. So we told them to sell it as is and get out of Dodge, because it's very hard to fix it when you can't get equipment back there. Here's a doctor house out there in Memorial, and the backyard was terraced. The Buffalo Bayou tributary. And built a house. As soon as they built it, the slope starts moving, start cracking the slab. The house had to be torn down. Global stability. When you build a structure next to a bayou or a ravine or a river or something like that, you got to check for global stability. You put the structure on deep foundation. You check for slip circle global stability below the foundation. You need a minimum factor of safety of about 1.4. So, swimming pools. We're building a lot of swimming pools all over the place. Most of these stuff not properly engineered. The largest pool in the world is in Chile. This is the pool itself. These are the hotels. The ocean. And it's a real $1 billion pool there. Here's some local pools out there, different shapes. Beautiful. This is a pool in Tanglewood. You can see one side. This is coming up in here. Usually the shallow end of the pool comes up due to presence of expansive soils. This side is coming up. This is Friendswood. It's a pool. This is one side of the pool. This is the other side of the pool. It's coming up, the shallow end. This is Memorial. That had a vanishing edge pool. It's a 40-foot drop. They didn't account for that. They started having global stability problems. The edge failed. This is a pool in West University. They were trying to clean it up over the weekend. They emptied the water. It drained. Hydrostatic pressure pushed it out of the ground, like 16, 17 inches. So they sued. And insurance is safe, sanitary, and livable. They're not going to pay them anything. Whenever you want to wash your pool and clean it up, you need to punch holes in the bottom of it to relieve hydrostatic pressure. Here's a pool coming out near Cypress Wood area. Tomball. Hydrostatic pressure pushing it out. Here's another pool. Bottom got to be nice and compacted. You put your steel in. Got chairs in it. You put your shotcrete in there or gunite. Basically, if you got expansive soils, you're going to have to remove the expansive soils, replace with non-expansive soils, or you do structural pool with helical piles or piers, or use chemical injection when you do pools. We have a whole presentation coming up on pools. I think it's coming up in August. So we'll send you notification. Affected trees on foundations. You asked me questions about the trees. Trees are beautiful, but they cause a lot of foundation problems. These are the root systems. This is what we call square root. So they finally know what the square root is. You can see some of the pictures of the pools. I mean, some of the trees are failing. Root systems are three-dimensional, up, down, lateral, all over the place. This is my house. You can see the tree going right through it. The vacation house. This is the house in Florida, the condo. And here's the backyard. You got your tree house. This is a tree hugger. See the trees? Most people like to have trees around their houses. When you put a house into place, make sure you take all the roots out, remove all the trees next to the house. If you leave the roots there, with time it decays, creates pathways for water to travel. Water to travel underneath the concrete slab and causes heave. These are where the roots used to be. Trees affect foundations three ways. One of them is called root heave. Actually, roots get underneath the structure, the wall, the slab, start lifting it up, trying to get moisture. See the root heave here? Sidewalks, downtown Houston. This is a willow tree next to this house. The house was moving up. They didn't know why. We excavated. We saw a 2-inch diameter roots going underneath the slab. It's a pine tree near Woodlands. The floor slab were heaving up inside the house. Jackhammered the bedroom. Pull out the roots underneath the bedroom. Roots going underneath the foundation, lifting it up. It's called root heave. Removing the slab, you can see the roots all over the place. Underneath the slab, trying to get moisture. When you put a slab on the on ground, you develop what's called capillary action. The area under the slab becomes wet. And the moisture, there's a lot of moisture. So tree roots want to go out there and get the moisture. So you cut out the tree roots, compact that soil with vapor barrier in, put the steel in and put concrete. Okay, this is the one that comes into design a lot. A lot of people screw it up. They don't understand root heave due to tree removal. If a tree dies or you remove it, the ground's going to heave if you have expansive soils. So this is a tilt wall building on Richmond Avenue. Tilt wall panel starts kicking out. The site was heavily wooded prior to development. Cut out the trees. All the root systems need to come out. No, nothing more than half an inch. When you cut that tree, the area heaves up. You want the soil is all dry in that area. It wants to rehydrate. So as it does that, it heaves up. This is point H when the tree was cut out. This is the building. The year was 1955. They cut out the building here near point H. The soil rehydrated. Point H took 32 years. It moved about 6.3 inches. Point F away from it moved about 1 inch. This is a building downtown. This is got this big oak tree right next to it. Tree's about 400 years old. The root system goes to a depth of 10 feet. The active zone, it affects 2H, twice the height of the tree, away from it. So if this is 50 feet, goes 100 feet on each side. This whole soil is brown, is highly desiccated. Once that tree dies, that desiccated soil wants to rehydrate. Everything out there is going to heave up, unless it's designed for it. Here's the moisture profile underneath the tree. This is 2H. Watch the height away from it. Tree stump over here, the depth of 10 feet. This is the cone of moisture deficit. This bowl starts heaving up. 100 foot away is 3 feet deep. So you build a building out there on top of the area where you cut a tree, that whole area is going to heave up. Yeah, I got a question. Frank. You're ahead of me, but you say, what and how does chemical treatment change the subsoil characteristics, particularly the PI? Give me a minute, I'll get to it in a minute. So the tree root systems extend past the drip line. So when you cut the drip line, it's going to try to restrict the root system going, but still root system expands past the root drip line. This is a house in Austin. Been around for a long time. The soil had PI between 50 and 60. They cut 3 root trees in the backyard. Within 2 weeks, the soil rehydrated, heaved up about 8.2 inches. Significantly heaved up to rehydrate. And they did research on this thing. You cut a tree and soil rehydration where there's a lot of moisture available. It takes about 5 years. The year 1, you get the soil rehydrates about 44%. Year 5, about 100%. So when you cut a tree, you build a structure on top of it. Ideally, you got to wait 5 years for it to rehydrate. If you don't have the time, you got to design for the soil to rehydrate. So you can do structural slab with deep piers, or you can do a chemical injection. You can do removal and replacements. Here's a tree next to this office building. If this tree died, this area is going to heave up, unless it was designed. Trees don't know anything about the fence. If your neighbor tree dies, this building here is going to move up. So the structural engineer should know about the presence of trees and trees dying. You got to design a structure assuming this tree is going to die one day. So if you plant a tree at the same time that you build a structure, with time that tree gets big, and soak moisture in the house is going to shrink edge of the building. Once you cut that tree or it dies, it's going to come back to the original location. If you put a building in an area where you have trees already there, that area that's been shrinking due to trees sucking the moisture, when the tree dies or you cut it, your building is going to heave up unless you design for it. So if you got these trees here, this house here, if it's not designed properly for these trees in the neighbor, once you cut these trees or they die, this house is going to move. Component number 3, short shrinkage due to tree moisture removal. So if you got buildings, you got trees right next to it, these are post oak trees. This whole edge of the building is dropping. Sloping towards the edge and cracking the slab. These trees are sucking moisture. The piers on this building were only 12 feet deep. They were too shallow, so the building itself acts as a floating slab foundation. It doesn't have a deep foundation system. The pier should have been 20 feet deep so that it doesn't go through that shrinkage problems. University of Texas has done research. If D over H, future height of the tree and distance, a D over H of 1, you can have 0.2 feet of shrinkage at this edge, 2.4 inches. So if you got trees, this is the city of Pasadena, you have these oak trees right next to you. If you go underneath the slab, you see these voids under the slab, sucking the moisture out. Risk of damage by different tree species. Oak tree, really bad. You want to put it 1H away from a building. That's 1 equal to future height of the building. So the building, future height of the tree. If your tree is going to be finally 50 feet tall, you got to put it 50 feet away from the building. Lime, 0.5. Common ash, 0.5. Plane, 0.5. Willow, 1H. Elm, 0.5. Hawthorn, 0.5. Birch, 0.5. Cypress, 0.5. So this presentation was called Trees from Hell. Some measures to prevent tree distress. Put the trees away from a building as much as you can. This distance, again, we talked about it, minimum of 20 feet or 1H, future height of the tree. Put depressions around the tree trunk so that water sits here, so the root systems do not have to travel, try to get moisture. Put sprinkler systems next to the trees. Put root barriers when you put the trees in the ground, so the root systems go downward, not horizontal away from the root systems. So they don't go horizontally to suck moisture. Plant stuff in the root barrier. Here are the root barrier systems. Put herbicides, root barriers next to the trees. The root system hits the herbicides and stuns them so they cannot penetrate them. They last 10 years. After that, they don't work. So root barriers are better, just a regular root barrier. Like that, it's better. This is a 15 mil fabric that you put in there. Put pots around the building. No plant areas. This is the Capital One building on Westheimer. It had a lot of movement. They were watering all these planters. You go out there, you look at it. The sides were cracking up. They had bed liners here. It was holding the water next to the foundation. All the tiles were coming out. There was sheetrock crack inside. Bed liners. We put pots there. Closed up all the bed liners and put pots in it. Stabilize the area. Sewer leak and plumbing leak. Somebody's asking how much a root barrier costs. I don't know off the top of my head, but you can call Due West or Ocean, Ramjack. Those guys, they'll tell you how much it costs. Not that expensive. Sewer leak, plumbing leak on the older buildings where you got plumbing problems, when you got leak, even on the new buildings. I'm looking at some buildings out there near Dallas right now. They put the plumbing inside the expansive soils heaving and pushing all the P-traps up and busting all the plumbing. And there's leak. If there's leak, it causes foundation movement. This is a leak due to plumbing, wetting the soils. You got to put in new plumbing in. You can do plumbing tests to make sure that if there's a leak there. You can do hydrostatic tests used for sewer lines. You fill the sewer for water for about 30 minutes, and you watch the water dropping. Video inspection. You can do video inspection of the storm sewers and sanitary lines. Water supply pressure. Pressurize the water lines 5 psi above the normal and hold it for 30 minutes. Here's doing the video inspection. You put in a clean out and you run it through. You look on the screen if there are roots growing in your pipes. You can also do non-destructive testing. Resistivity. When we do soil testing, it's a one-dimensional deal. If you want to know three-dimensional what's going on underneath your slab, you can do what's called resistivity systems. You put probes in the ground, run electricity on it. This is inside the building. We want to know if there's water under the slab. You put the probes in, and you can see resistivity here. High resistivity is concrete, hard soil. Low resistivity is water. And you can see the bath of water underneath the slab. Here's the slab, concrete, water. You can do ground penetrating radar. GPR uses an antenna that transmits electromagnetic energy like cell phones do. A receiver located within the antenna receives the reflected signals. You send the signal. If you see something in here, reflects it, you know something is in there. You can pick the areas of high moisture, voids. That's the GPR. You can see the pipes on the ground. You see anomalies, typical voids. Here's the building with the GPR on it. We had this is a shows anomaly here, ground void. The pink area is the voids under the slab. The blue areas is the high moisture areas. The pinks are the voids. High moisture, high moisture, high moisture. So you can run the GPR, and if you can see there are voids and high moisture under the slab. Geoforensic of Voss Road. If you go to Voss Road, you see voids under the slab, under the paving. They fixed it though, by the way. The Voss Road was built on top of a ravine here, part of Buffalo Bayou system. They put the Voss Road on top of it. The area settled after they built it. We did GPR on it. And we find all these voids under the concrete paving. find areas of high moisture and voids. The pink areas are the voids. The blue areas are high moisture areas. When you do GPR, you can find where the steel is in the concrete. You can actually run it through it and find on the screen where the steel is, the sizing and spacing. If you run it on a slab, you can tell the high soil unit weights. If the high unit weights of the soil 115 here, the low soil unit weight of 80. That means the soil is poorly compacted here underneath your slab. You can pick that up using GPR. You can also check the soil unit weight, the slab unit weight. Concrete is 150. These areas are 150. These areas are about 145. The blue areas are about 130 unit weight. Too much water. You can use infrared based on temperature gradient to see if there are problems. Infrared, since because of the temperature, it picks it up. Over here, you got an under slab leak. The area, it's a hot water leak here in the kitchen sink. Right here, you can see a blue area here is leaking because of the temperature. You can see that. It's cooler. Hot water heating again. Right here is a leak out there. You can do exterior surveys. You can check for stuccos using thermal imaging. You can look for columns. You can see if the insulation is missing. Water is coming around the light fixture. So this is the infrared technique. Geologic faulting, we got faults all over the Houston area. You got to check for faulting when you build a building. You build a building on top of a fault, goes crack to paving and goes right to the building here. This is a house sitting on top of the fault. This is the shear zone. This is the up-thrown section of the fault. This is the down-thrown section of the fault. Droughts. Sometimes we get a drought conditions in Houston, in Texas. This is 2011. We had a major drought. This was really a drought, basically a severe condition, where we lost water in Lake Houston and Lake Travis. Lake Travis. Look at the river here. It was all dried up. That's 2011, 2010 to 2012. This is the rainfall in 2011. We had only 24 inches of rainfall in Houston. Average rainfall in Houston is about 50 inches. Again, 2020, about 44 inches. 2021, about 51 inches. 2022, 37 inches. 2023, 41 inches. Rainfall affects stuff. Today, 2024, about 10, 11 inches of rain. We got excess rain right now. This is a drought monitor in 2020. You can see parts of Texas in drought. D4 is the exceptional drought. 2021. See parts of Texas in drought. Panhandle. 2022. Drought. 2023 drought. Harris County was okay. 2024, we have droughts in part of Texas. This is where the fire is. This doesn't look real bad. So when you have a drought situation, the soil becomes very dry. And the soil properties, when it gets really dry, the soil becomes like vapor, the water in the soil, the moisture. So there's no liquid water in the soil anymore. That happens at about what we call suction level of 4.5. So suction is basically measure of free energy. That's the soil property. Soil suction may be described as the ability of a unsaturated soil to attract and retain water. Here's a foundation performance after heavy rainfall and then droughts. Average rainfall in Houston is 50 inches. If you build a slab when there was a lot of rain and then we get a drought, this is number of years and of course drought. You got a slab, it was wet, and you get a dry condition. You get edge shrinkage, or what we call center lift. The house cracks up in the middle like this. If you do a house after a drought, so when we have a drought condition, low rainfall, and then also a bunch of rain, you got edge lift. The bottom goes in tension, the top goes in compression. One of the ways you can tell if there's a problem is by looking at aerial photos. The houses over here, they had to be fixed. There was a ravine there. They backfilled it with loose material. They didn't compact it. They built all these houses. They had problems. This is near the airport. This is another house out there, Eagle Spring. They built houses on top of ravine. Some of these houses had problems. You can see on the quad sheet the ravine. Forensic engineering courts. Less than 10% of the cases go to in U.S. go to trial. Most cases settle after the lawyers make their money. For cases going to trial, forensic engineer plays a major role. So when you do forensic evaluation, you got to look at things from different angles. For example, if you look at Mount Rushmore, this is the front, and here's the back. So this is it. Send me pictures. If you got pictures of failures and all that, I would appreciate having pictures. So send me pictures of the stuff. This presentation is going to be on YouTube, so you can go watch it again and again. You're going to get a link for this thing and certificates of attendance for your PDH. We got a program evaluation. I don't know if it works or not, but I'm going to try to do a poll. And I don't know if you're going to get it or not, but if you do, go ahead and fill out the full poll. If you need to reach me, my email is de@geotecheng.com. My number is 713-699-4000. We're going to have a bunch of seminars coming up. So if you registered, you're going to get our emails. You're going to get your PDH hour within a week. Questions? Okay, somebody says that was a lot of information. Thanks. You're welcome. Any other questions? Steve Beckentroth. Thank you, Dave, for this session. Good to hear from you, Steve. John Whitman, thank you for your time. You're welcome. Yoshira, thank you very much. Great presentation. Okay, somebody asked me about chemical injection. Chemical injection, when you inject, that's another presentation, by the way. But if anybody does chemical injection, you got to go in there and what it does is chemically change the soil. Soil has got a clay double layer, which has got the negative charge on it. Chemical injection reduces the negative charge on the clay layer, on the clay platelets. And so what happens is the chemical injection, which is a light grade like sulfuric acid, goes in there and reduces the negative charge and removes calcium and potassium, put sodium and potassium and put calcium in it. It's called a cation exchange. So the cation exchange reduces the heave that occurs on chemical injection. Again, that's another presentation. Any other question? Well, I'm around. You got my email. Send me an email if you got questions. If you got questions about the deflection, I'll send you the right guy that can explain it to you about the deflection criteria. Comment, homeowners and realtors should watch this. Yeah, I agree. And Vora Todd, Love the pictures. Anwar, send me some pictures. Any other questions? Look forward to upcoming presentations. Okay, well, you all have a great day. It was a good presentation. I enjoyed it. And I'll see you guys around. If you need geotech work, material testing, please contact us at Forensics.